Thanks very much. Thank you. I always get nervous when people clap when you get up and you haven't said anything. The normal reaction to this is I should sit down, because it won't get any better than that. Let me first start out by thanking you for an opportunity to talk this afternoon. I hope that you aren't expecting an extremely deep, comprehensive discussion about architecture. If you are, you can go to sleep now, because I certainly don't anticipate trying to do that in the time I have available. What I do want to do, though, is to try to underline maybe some principles, some notions, some ideas, some issues that I hope all of you will keep in mind as you struggle to figure out how we should design and build such a complex system. It is a massive transformation in many respects of what we have lived with for the last, roughly speaking, 100 years. So you are undertaking a remarkable enterprise which could have extremely long-lasting impact on the way in which not only American society, but perhaps societies around the world experience their use, not only of electrical power, but other resources as well. I wanted to begin by calling this Only Connect, and to draw attention to a literary phenomenon, a man named E.M. Forster. If you don't recognize the reference, let me encourage you to Google Only Connect and Forster and learn what this was all about, a philosophical point of view that many solutions to our problems require us to connect with each other. And certainly in the process of developing standards, it is the connection between us and our shared understanding of the problem space and our willingness to give credibility to each other, to trust each other's motivations, to want to get to consensus. Everyone may be motivated by different things. Some of them will be pecuniary motivation, some of it will be corporate, some of it may be personal. But in the course of trying to establish standards, one of the things that's very important, I think, is that we start out from the premise that people's intentions are good and credible. Now, I know that sounds a little Pollyanna, but it's very, very hard to do the standards without at least starting out on the presumption that the other guy wants as much as you do to come to some kind of consensus. Of course, we all understand that sometimes that's of the form, I want to come to consensus as long as you agree on what I want to do. That's, of course, the place where leadership is needed in the various working groups and PAPs and the like. So please do look up E.M. Forster. By the way, he also wrote another book, which I draw to your attention, called The Machine Stops. And this was about a society in which everyone was housed at home and fed remotely at home. They never went anywhere out of their homes because they interacted with each other through this machine. Now, this was written around the turn of the previous century, so in the 1900s or so. And The Machine Stops is all about what happens to that society when this machine doesn't work anymore. And we don't want that to happen with the smart grid. We don't want the grid to stop. We don't want the systems that we are relying on to stop. So you should read a little bit about what the side effect of that was sociologically. Let me start out by taking you back into history for just a moment. This is the first 4 nodes of the ARPANET project. What many people may not appreciate is that it was motivated by resource sharing. The Defense Department was sponsoring many computer science departments around the United States to do research in artificial intelligence and computer systems design, programming languages and the like. And every one of the institutions insisted that they had to have a world-class machine in order to do world-class research. And so they would say every year they expected to get a new computer. Now, back in those days, in the late 60s and early 70s, machines were millions of dollars. They occupied 1 or 2 or 3 rooms, needed special cooling and everything else. So even ARPA, with its budget, could not afford to buy a brand new machine for every one of these dozen or so departments. So they said, why don't we find a way so they could share? And to do that, they decided to go down the path of building a packet switch net, which was not at the time the conventional wisdom. The conventional wisdom at the time was you built networks using circuit switching technology, just like the phone network, but that didn't look like it would be responsive to the kind of dynamics of computer networking or computer communications. So this was the first 4 nodes, and it really was motivated not by building a network to survive a nuclear attack or anything. It was to share computer resources among a collection of people. Of course, as we got further into that exploration and packet switching worked well, the internet was designed and built and propagated. And here you see an automatically generated view of the connectivity of the internet, different colors for different autonomous systems. And the point here that I want to emphasize is that this is not a centrally controlled system. It's very distributed, it's very collaborative. People voluntarily connect to each other on this network. The reason they do that is that it is, from their point of view, for a variety of reasons, beneficial to be part of that system. So it is highly collaborative and highly dependent on people's willingness and agreement to interconnect in this way. And I would suggest to you that a successful smart grid effort will have that characteristic as well, that it's important that there be reasons why appliance makers, power generation and distribution agencies want to interconnect and engage in the use of this new technology that you're working on. So collaboration is going to have to be an important element. This is not going to be something we can force on anyone, no matter how hard we try. This is relevant to another point I want to make in a moment. This is the rate at which computers have been added to the internet. It's slightly misleading in the following sense. These are the machines that you can actually see on the public internet. There are probably many more that are hidden that you can't see in the public net because they're behind firewalls, or in Google's case, we have a lot of machines in our data centers that don't actually appear on the network with IP addresses and public domain names. So the actual number of machines on the net is larger than this, but the doubling rate in the last 16 years or so has been about doubling every 5 to 6 years. There was a time in the late 1980s when the rate of growth was more like 100% a year. But when you get to the 750 million machines or so that are visible, plus the others that are not, the doubling rate, understandably, has diminished. But still doubling every 5 to 6 years implies a substantial amount of demand for internet address space. Here are the actual statistics: 732 million estimated machines on the publicly visible network in January, and 1.8 billion users on the system. The other statistic, which is relevant in my view, is the number of mobiles that are in use, 4.5 billion of them, of which some fraction, I don't know how many, 15 to 20%, probably have internet access of one kind or another, and some are going to consume internet addresses as well, even if it's an ephemeral consumption. The implication of this is that internet address space is being consumed at a fairly high clip. And in fact, this is not a picture of today's Dow Jones Industrial Average. At least I hope it isn't. This is simply the diminishing number of IP version 4 addresses that are available to apply in the public internet. The choice of 32 bits was something that I chose in 1977 when I was still at the Defense Department, and this was a project that was only 3 or 4 years old, and with no clear indication that it was going to be successful. And so the question is, how much address space do you need to do an experiment? It seemed to me that 4.5 billion unique terminations was enough for an experiment. The problem, of course, is the experiment didn't end, and so here we are. It's 2010. And we need now a new, larger address space, and that's provided by something called IP version 6, which was standardized, in fact, in 1996. So quite a long time ago. The belief that we needed a larger address space emerged out of the Internet Engineering Task Force as early as the 1990, 91, 92 period. But it's took a while to come to agreement about what those addresses and the rest of the packet format should be. And it's been incredibly slow to implement because most people haven't felt the pressure that the run out of IPv4 is going to apply in the next year or so. The expectation is that the Internet Assigned Numbers Authority will run out of address space to hand out to the regional Internet registries sometime in 2011, probably sort of in the fall or so. And the regional Internet registries who hand out Internet address space to the Internet service providers will probably exhaust their remaining allocations sometime in 2012. And although that might seem to some people rather far away, it takes time to implement these new protocols in parallel with IP version 4. We have experience with this at Google. We've implemented IP version 6 together with version 4, and it's taken a couple of years of work, not with a huge number of people, but with great care, finding all the places where the assumption that IP addresses are 32 bits is replaced with the recognition that it might be 128 bits of address and not 32. There are other things happening to the Internet, and I don't mean in this presentation to go into very much detail at all, except to say that we're seeing the network allow non-Latin characters in the domain names, for example, and there is heightened attention being paid to security on the Internet, partly because it's very clear that there are a lot of bad things that can happen in the system. So domain name system security has become a very important thing. The digital signing of domain names, especially up at the root zone and further down, is in the process of happening. I should say that these concerns about security are also very much applicable to the smart grid for the obvious reasons that we rely every single day on electrical power, and if we change the way in which that power is distributed, consumed, controlled, then the security of that system is important to us, not only for the quality of life that we have, but also for our economic security. There are a set of other things happening. Sensor networks are coming online onto the Internet, again consuming address space. The smart grid itself, because some of the discussions have been to make use of the IP protocols in part of the smart grid, especially in the residential and industrial sector, will again consume address space. And finally, devices of all kinds are coming onto the net, some of them mobile and some of them not, but all of them becoming a part of this panoply of connected things, which brings us to the notion of an Internet of Things. These are objects that communicate with each other, not necessarily, and with us, and possibly with third parties that may be managing them, providing them with advice, consuming information produced by those devices and regenerating it and analyzing it, providing it to us for our information. One of the things which I believe is incumbent on all of us as we think about the smart grid system is that we introduce strong authentication into the fabric of the communication system. We did not do that in the original Internet design, and one of my excuses is that the technology to do it didn't exist at the 1973 period when Bob Kahn and I were first doing the work. Public key cryptography didn't even get written up in public form until 1977, which is just about the time that the Internet protocol architecture was being finalized. So we didn't incorporate strong authentication into this, but I would say that as we look at the smart grid and as we look at the Internet evolution, that strong authentication is really important. We don't want things in the system that aren't supposed to be there. We don't want the controllers to take information from something that the controller doesn't recognize as something it should be paying attention to. And by the same token, we don't want a device to respond to control from something that it doesn't think is authentic. And therefore, we need to introduce these stronger authentication mechanisms using public key cryptography and certificates, for example. We also are going to need unique identification for a variety of things, not just at the device level, but up and down in the architecture where individual users or other controlling systems have identities that can be uniquely determined. And I think in addition to all that, for many of the devices that we connect together, they may be in environments where connectivity is not assured, particularly if we're using radio-based connections, which may very well be an important part of some of the smart grid implementations. So mesh-like capability where the devices actually help each other moving data around may turn out to be an important part. We as a group trying to develop the smart grid interoperability concepts don't necessarily have to invent all of these things, but we should be cognizant of their existence. We should take advantage of things that other people have done in order to make of the smart grid a more robust and resilient system. There are an awful lot of devices that have already shown up on the internet, and I have to admit to considerable surprise. I certainly never anticipated that someone would want to connect a refrigerator up to the internet, although there were jokes told in the 1970s about ToasterNet, and some of you probably will remember that at one of the interop shows, which is interoperability of the internet, somebody actually did connect a toaster up to the net, and you could send an SNMP control packet to say how burned you wanted your toast. But these things have evolved over time. Picture frames, as many of you probably know, are on the net and can download images from websites or things that you've uploaded with your digital cameras, or telephones that look like telephones but are actually voice over IP devices. And the guy that I frequently talk about is the fellow with the internet-enabled surfboard, whom I haven't met. I understand he's Dutch, and I imagine him sitting on the water waiting for the next wave, thinking if I had a laptop in my surfboard, I could be surfing the internet while I'm waiting for the next wave. So he put a Wi-Fi server back at the rescue shack, and now he sells this as a product. The sensor nets, I am persuaded, will be prevalent in the internet environment, in part a consequence of what you're doing, because a good portion of the motivation behind the smart grid is in fact to sense utility, use of electrical power or conditions that demand the use of electrical power. I have a sensor network at home, very proud of this. It's a commercial product, so it's not me in the garage with a soldering gun. This is a company called Archrock, which is out here in the Bay Area. And they make a commercial sensor system that, in my case, picks up temperature, humidity, and light levels in every room in the house, and every 5 minutes that information is recorded in a server. I know that sounds like something only a geek would do, but the honest fact is that I was interested in getting raw data, which I could refer to later, like at the end of the year, to see how well or poorly the HVAC had been distributing heat and cooling. And I wanted real engineering information rather than anecdotal information, so that someone who was trying to make the system work well would have solid information. So this system is collecting this data every 5 minutes. One room in the house is quite important to me. It's the wine cellar, and this needs to be kept below 60 degrees Fahrenheit and above 50% humidity, so the corks don't dry out. So that one has been alarmed. And if the temperature goes above 60 degrees Fahrenheit, I get an SMS on my mobile. And this actually happened while I was on my way to visit the Argonne National Laboratory for 3 days. As I was walking into the building, my mobile went off. It was the wine cellar calling. And it said that the temperature had just broken through the 60-degree Fahrenheit barrier. And sadly, my wife was away for 2 weeks, and no one was home to turn on the cooling system again. So every 5 minutes for the next 3 days, I kept getting this note saying your wine is warming up. I finally got home, and it was 70 degrees in the wine cellar, which isn't not a disaster. But I did call my friends at Archrock, and I said, "Do you make remote actuators?" And they said yes. So this project now is to put a remote actuator in with strong authentication so that the 15-year-old next door doesn't reprogram the house while I'm away. But I noted that because I could see light levels changing in each room, that I might be able to tell if someone had gone into the wine cellar while I was away. But of course, they didn't know what they had done. So the next idea is to put an RFID chip on each bottle, and then be able to do an instantaneous inventory of all the bottles in the wine cellar in case anything had left the wine cellar without my permission. Of course, one of my engineering friends pointed out that there was a flaw in the design because you could go into the wine cellar and drink the wine and leave the bottle. So this is why we have smart grid, priority action panels and engineers to evaluate designs. So we're going to have to put sensors in the cork. And as long as we do that, we might as well do something to sense the esters in the wine to see whether it's ready to drink. And before you open the bottle, you interrogate the cork. And if this is the bottle that got up to 95 degrees or something, that's one you give to a friend who doesn't know the difference. So this is a small sample of the kinds of things that we would, I think, regularly expect in residences and certainly in industry, in buildings around the United States and elsewhere, to gather more data about environmental conditions and how well we are meeting them. So I want to make one point, which I made earlier today in the governing board meeting, and which got a certain degree of resonance, and that is that we should not be confining our thinking as we think about the architecture to just electrical power and the consumption of electrical power or the control of demand for electrical power. Please think about this as a system which is accumulating information about our resource consumption, including oil and gas and water and other important resources. Because in the end, if our intent is to optimize the way in which we use these resources, we may actually have a multi-commodity optimization to worry about. We may need to know more about how we're consuming resources and when, not just electricity, but some of these others. The implication of that is that the architecture and the means of expression of our consumption and use or pricing and all these other things should be generalizable so that we can deal with some of these other commodities. I'm not saying we should go solve the multi-commodity problem now. I'm certainly not saying we should figure out what all those things should be now. We have a big enough and hard enough problem with the smart grid, electrical grid, but I think we should be cognizant of the utility of thinking more broadly about what it is that we are doing. I've been told that the Chinese or the Japanese have something called the smart community, and they are speaking of multi-commodity measurement metrics and the like. So they are already in some ways ahead of my thinking anyway. So I put that on the table not as not to throw a grenade into the conversation, but to say that generalizability, extensibility is really important in the design, and we should keep that in mind. So the smart grid, in some sense, is only the beginning of thinking about how we account for our consumption of resources. So the key ingredient in all of this, in my view, is information. Because in a sense, it's not possible to manage our use of power, to control the distribution of power or other commodities, except for having the right information to know what we should do. When am I using it? How much am I using it? What are the prices? And when are those prices changing? All of that is just information. And so figuring out how to present or represent that information, how to share and distribute the information, how to assure that parties who can usefully benefit from that information are able to get it, is all a part of the kinds of architecture that we should be thinking about designing. So there are some things that I believe would be desirable in the architecture, I won't even call them principles because that sounds too deep, but just simply features that we ought to keep in mind. This is absolutely not a complete list at all, and I'm sure that you'll come up with many more ideas than I have. But one thing is adaptability in the design. I don't think that any single communication method will be sufficient to link the various devices that we want to monitor and control together. So we can't just pick one communication medium in order to make this work. Things get moved around the house. Things get moved from house to house or from office to office or moved around the plant floor. So we may discover that any particular choice of medium only works for a subset of the places where we want things to be. So we are, I think, compelled to think about how to design this system so that the communications can go over a variety of different physical layers or MAC-PHY layers, whether it's a wired Ethernet or a power line or a serial channel or various wireless options. And I'm sure I deliberately have not listed all because I don't know what they all are. And some of them are being invented literally as we speak. But we should be very conscious of the need to allow devices to move from one communication regime to another at need, depending on what works for purposes of managing and monitoring these things. One possibility is to design into the appliances that we're trying to track a way of easily replacing the communication capability with something else if it's needed. We could get into enormous arguments, and probably some of you already have, about whether that's possible and how to do it and what impact does it have on the cost of things. Flexibility often comes at a price, but the one thing which I believe is inescapable from my point of view is that we won't be able to pick one or two, one wired and one wireless means, and assume that that will work for everybody for all situations. And so we need to think more carefully about how to be adaptable. The other thing that's important is that devices, many of them are going to last for a long time. We don't replace a lot of the equipment that consumes electricity very often. Water heaters don't get replaced very often. They usually get replaced after there's a catastrophe and something leaks in the basement. So the same is true for a great many of the things that consume these resources, an oil burner or a gas burner. So they last for a long time, and one of the questions is how well can they be adapted to changing circumstances, given that they are not replaced with great frequency. So again, this, for me anyway, reinforces the need for adaptable architectures. Plug and play, which is a sort of an overused term, but I think it's very important, especially if we're considering consumers who are not necessarily experts at all in communication networking or our network architecture or debugging or anything else. So if this is going to work at all, it's going to have to work in a way which is largely transparent to most of the users. You'd also like it not to be the case, I think, that in order to install something which is part of the smart grid program, that you have to send a person out to do configuration and debugging and the like. Well, the implications of that are actually fairly dramatic, because it means that these systems have to have self-organizing properties. The devices have to find each other. The monitoring systems have to find the devices. We have to distinguish the devices they're supposed to monitor from the ones that they aren't, like the ones that are next door. And for some of the communication alternatives, there isn't any guarantee that you won't encounter devices that are not supposed to be a part of your local universe. So figuring out how to do this kind of self-organization in a way which is secure and also maintains privacy and so on is a non-trivial exercise. And some of you are going to be confronted with that because of the various groups that you're working with. This mutual authentication idea, and again, strong authentication notions, appeals to me very much because it's important that we are able to know whether we have a consistent system with devices that recognize each other and recognize their controllers and the like. So on top of which, it would be important to know who is allowed to have access to the information either generated or consumed or held by these devices. So we need to have ways of doing authorization and authentication that protect people's interests. A rather interesting situation is that some of these devices may move from party to party. I mean, you sell things at garage sales, or you shut down industry and people buy things at auction. Having the ability to reset and have the system go through a self-organization is very important. So again, please think about the requirement to do that, because it's not the case that having acquired something, it will be kept by the acquiree or acquirer forever or for the lifetime of that particular device.